integration fx dx was in some way the area under curve, right? But where does this the so it's basically integration came from evaluation of area, right? But then evaluation of finding area, that has long history. So it starts from around, excuse me. Yeah, it starts from Greeks around 500 to 450 BC. They try to find area of circle first of all, but they actually think, yeah, I forgot the name of a Greek who tried it. Yeah, so the point was basically you look at a figure and try to capture that figure by putting triangle or rectangle and capturing the whole thing together. That was the idea. So this is called method of exhaustion. So by nicely geometric figure, for example, if you look at circle and you first add a triangle, then add more triangle to get a hexagon, or increase the edges of the polygon to get the circle. So as you increase the number of edges, you will actually, of course, the endpoints lying on the circle, you will be actually going towards, the area would be going towards the area of the circle. So this method was called is called method of exhaustion. It was right. So antiphon, right. Then Eudoxus, I think, written these things properly, and it actually went after him. And of course, then Euclid used it in his book Elements, right? Elements is one of the oldest book, still useful, and still people read it in several contexts in schools. So yeah, and then these things went on, and then development of calculus in 16th century, and then coming to the integration. So the integration for continuous function was rigorously done by Cauchy, and then of course the nice class of functions he has assumed. Then of course Riemann tried to extend this definition to more general class of functions. That is what we'll be dealing with. And then Lebesgue actually extended further on this using measure theory. All right, so let me begin the presentation.
Sir,
Yes.
you mentioned that the step function is Riemann integrable, but since the step function doesn't satisfy the intermediate value property, it can't be the derivative of any function, right?
What did you say?
You mentioned that the step function is Riemann integrable, but
Right.
since the step function doesn't satisfy the intermediate value property, it can't be the derivative of any function, right?
Right. True.
So the set of Riemann integrable functions is actually like far larger than the set of functions which can be derivatives.
Right. So usually what you do in school, what you did in school is to find antiderivative, right? So the function which integration fx and f is in ddx of something, then you integrate it and get back uh, get back the value. In this case, yes. So step function is of course not a derivative of any function. So, but still it is Riemann integrable. Geometrically, it is very easy to see because I mean you can, maybe I'll just draw it. So today is 24th. Right. So if you draw the step function, let's say start with this one. So on. So you can clearly see here what do you want to find. Is the area of this one, right? So we want to find this, some of these areas, right? So it is clear from the picture that the areas can be found and it is very easy to find, right? And you see here, we are actually looking at the step functions. Here, what is it? Look at this one, LPF and UPF. What are this? So you can consider the step functions on xj minus 1 to xj as mg, right? And you are looking at this kind of stuff. So let me tell you again. So uh, let me draw the curve. So how actually we are using step function to define integration. Let me say that. So um, so suppose this is the point A and this is the point B, and we have taken few partition. A is x0, this is x1, x2, x3, and this is x4. All right. Now suppose our graph is of this form. Something like this. All right. So what is this step function? this is M1, right? This is M2, this is M3, this is M4. So now if you look at, so this is x-axis, this is y-axis. Now if you look at M1 times x1 minus x0 plus M2 times x2 minus x1 plus M4, maybe I should write it because only 4 things I have taken. M3 times x3 minus x2 plus M4 times x4 minus x3, right? So this is U P P F, where P is the partition A equal to x0, x1, x4, which is equal to B. All right. Now, if we want to look at the lowest sum, so it would be maybe should take a different color. Right. This one, yeah. Here, not this one. Little bit upward. It is coming here only. Like this. Here, like this. And here, like this. So this is small m1, small m2, small m3, small m4. So LPF for this same partition is small m1 x1 minus x0 plus small m2 x2 minus x1 plus m3 small m3 times x3 minus x2 plus small m4 x4 minus x3. So this is, you see, so the point is the upper sum in the upper and lower Riemann sum, we are considering certain step functions, right? Right? Is this clear? So do you see the step functions? We are actually using it, right? Yeah. So step functions will be Riemann integrable by definition because you take the partition, and if you look at endpoints as the partitions, you will get that the the lower and upper, I mean small m1 equal to capital M1, small m2 equal to capital M2, and so on for step function. So if your function is a step function, then lower sum and upper sum are automatically equal. So is this clear? Yeah. For every partition which contains the endpoints of this interval where the steps are there. Is this clear?
Yes, sir.
Yes. All right. So we are using step functions in the definition of integral. Okay. So now today we'll actually prove a theorem which will be very crucial. So the main idea here, the integration you have seen in first year as well. So why the hell is integration in the second year course also? The viewpoint is changed. Instead of looking at the evaluation of the integral, we are first question we ask, what are the class of integrals, integrable functions, for which you can, of course, for which you can integrate. You can integrate. Whether you can integrate explicitly or not, that is a different question. We are not looking at that. We are looking at whether the integration as per the definition gives you a finite quantity for what kind of function are this. So that is the question we are asking ourselves, and that is the question Riemann also have asked. So let me show you uh, the paper by Riemann where what exactly he had asked. Yeah, yeah. So you see this line. He exactly asked what does this mean, and he actually defined this one. And this is the tagged points. These are the tagged points. And later on, he actually gives a, of course, not so precise proof of what functions are integrable in this sense, in his sense of this one, in this sense. Yeah. Yeah. So we'll come to this one. So this one, secondly, the range of validity of the concept. In which cases can a function be integrated? In which case can it not? Right. So these are two questions we'll be looking at in first of this interview in our discussion of integration. And this is what, and we'll go through this proof. I'll also present in the end in very precise formulations, not exactly this one. Okay. So the question is this. Question is not to evaluate the existence. All right. Right. So we have for a partition we can look at the upper sum and lower sum here, but now and then we did look at the supremum and infimum here, right? Now the point is how to achieve the supremum. Let's formulate something. a way to proceed towards that. Right, so what does it mean that supremum this one is equal to infimum this one? So, and what would be the infimum? Because given an interval, you have uncountably many partitions. So, how to work with them, right? Work with all the partition. So, for that, we need a concept called refinement. So, definition: refinement of a partition. A partition P of AB is said to be a refinement. Sorry, partition P tilde, let's say, refinement of a partition P if the points in the partition P, right? So we already we did look at this one. What does it mean? It means actually the points x0, x1, dot xn, such that this holds. So if P is subset of P tilde, right? So points in P should be contained in P tilde. So for two refinement, we have the notion of common refinement. So we give that definition as well. Given two partitions P1 and P2 of an interval AB, we say that P tilde is their common refinement if P1 union P2 contain in P tilde. All right. So the point is, you have, suppose this is an interval AB, and suppose this is partition. This partition, let's say x0, x1, x2, x3, so on, xn. This is x0. And let's look at another partition, y1, y2, y3, yn minus 1, so on. So now if you look at the union, taking this A, comma, y1, x1, y2, x2, and so on, this will give you, this will be a refinement of both this x0, x1, xn, and y1, y2, yn. So union is always a refinement. All right. Reunion of two partition is a common refinement for both. If you want to increase more, you can add few more points here. Few more points here. There's no problem. All right. So now what happens to this upper sum for the refinement, right? So why do you care about refinement? So this does the obvious thing. Let me write it as theorem. Let P tilde be a refinement of partition P of the interval AB, then the lower sum actually increases, monotonically increases, and the upper sum, what should happen to upper sum? Yeah, will it increase or decrease?
Decrease.
Decrease, right? We are looking at infimum, right? Infimum of upper sum and supremum of lower sum. So we want to find a way towards the supremum of upper sum, supremum of lower sum, and infimum of upper sum. So this one would decrease. Right? And the proof is not very difficult. Let me give a picture, and the things are properly written in the notes. So suppose you have partition, you have an interval AB, and you have partition A equal to x naught, x1, x2, x3, xk, xk plus 1, and this is xn. Okay, and your p tilde, assume you have just added 1 point y here. Okay, so p is x naught, x1, xn. X naught is equal to a, xn equal to b, and p tilde is x naught, x1, xk, y, xk plus 1, xn. This is a, this is b. See, we have this one, this x naught less or equal to x1 less or equal to xk less or equal to y less or equal to xk plus 1. Less or equal to xn. This is a and this is b. So how do we manage? Right? So the interval, subinterval, small subinterval that we need to look at is This one, suppose this is x k and this is xk plus 1, and you have the graph. Suppose you have the graph like this. So other parts actually all remain same, right? Lower sum as it is, upper sum as it is. Here we incorporated a point y, right? And so we have to divide this into two subintervals, right? So here it is. All right. So previously the maximum and minimum was, well, let me put a little bit this side, because that would make yeah. So we have this might not be in the middle. Why? So I could be any point. Right. So let me do this one. So the lower sum and upper sum. So what was the lower sum? So P LPF was summation mj xj minus xj minus 1 j from 1 to n, right, where mj is infimum of f x on xj minus 1 xj. All right, this was the lower sum, and upper sum was for the partition P is summation j equal to 1 to n capital MJ xj minus xj minus 1, where mj is infimum xj minus 1 xj. Sorry, this is supremum of fx. Now you want to look at what I said, this L also, this u. Yeah. Now we want to look at L of P tilde f. So P tilde is just adding 1 point to P in this interval from xk to xk plus 1. So this will be sum j equal to 1 to k m mk, sorry, mj xj minus xj minus 1 plus. So this it went until xk. So now this one you have this partition xk comma y. Now this will be summation, not summation, this will be m into x, sorry, this is y minus xk plus m into, this is m1 and this is m2. Oh, sorry, m1 and m2 is there, so let me write it m and m tilde xk plus 1 minus y plus again sum j from k plus 1 to n mj xj minus xj k plus 2 2 2. Yeah, right. So this is remaining on this part. So there is this part and this part. So this part, course, whatever the partition corresponds to is this one. Here we considered this one. I'm saying what is m and m tilde, and then this part corresponds to the partition, usual partition from this, where m is infimum of fx on xk comma y, and m tilde is infimum of fx y to xk plus 1. Is this clear? Is this clear?
Yes, sir.
All right. So now we need to compare, right? So what was it on infimum of fx on xk plus xk to xk plus 1? So how does it compare with m and m tilde? So this was mk, right? Mk plus 1, right? So how does this one compare with m and m tilde? Is it greater than of this or less or equal to this?
Greater than.
You have infimum on a bigger interval. Is it greater than the infimum on a small interval inside that?
Smaller than.
Sure, this is less or equal to. So infimum on a bigger interval tend to be smaller, right? Because the other one is a part of it. M. And mk plus 1 is less or equal to m tilde also. Right? So here in this sum there was mk plus 1. Here there is no mk plus 1. Right? It retained it at mk here and then started again mk plus 2. And in between there was two things, m and m tilde. So L P tilde F is greater or equal to, if you replace mk plus 1 here, right? Summation j equal to 1 to k mj xj minus 1, right? And then this mk plus 1 y minus xk plus mk plus 1 xk plus 1 minus y plus sum j from k plus 2 to n mj xj minus 1. So which is, this is nothing but, you see mk plus 1 gets common, y gets cancelled. So this is L P tilde, sorry, L P F. So similarly, instead of this one, infimum, similarly, one proves UP F. In this case, this will be greater. UP tilde F. Because now when you break here, M and M tilde, you write capital M and capital M tilde. Capital M will be supremum of Fx on the smaller interval. And here M tilde will be supremum of Fx on this interval y2 xk plus 1. Now, what happens to supremum? If you look at big interval and smaller subinterval, how does they relate it? Yeah.
Supremum on the bigger interval will be greater than equal to.
Right. Supremum on the bigger interval is greater or equal to the supremum on the smaller interval. That property is used, nothing else. And the proof is done. So this is an exercise. And you now to get the general, so this one we have done adding 1 points. So that the procedure, the same procedure can be followed to add finitely many points to P, right? And still have the same thing. So this is also an exercise. So if you add 2 points, then what happens? You add one first and you add one more first. You can also do these things together, right? So try to write the proof having finitely many points added. All right. So now I want to state and prove an important theorem. So this is very important. Well, let me give a remark before that. So this is very crucial, right? Here, this one for a refinement. So we keep on refining a partition. So consider a partition P, and so this is a remark of AB, and keep on refining it. So how do you refine? It's refinement. Suppose P containing P1, containing P2, containing P3, and so on, containing PM. These are refinement. So what do you get? LPF will be what? Less or equal to P1F. Less or equal to. That's what we got, right? See, the refinement is bigger for lower sum. P1, P2F, LPM, F. Right? Similarly, and for upper sum, you have the opposite inequality. Right? So now one is monotonically increasing, other is monotonically decreasing. And we want to capture the limit, right? So will that converge? The lower one, lower sum? So if you keep on increase m belongs to natural number, so will it converge? You need an upper bound for this, right? Yeah. So a monotonically increasing sequence of real number, when it converges, when a monotonically increasing sequence of real number converges,
When it is bounded above.
right? And you see here we have PM both, right? So lower sum is always less or equal to upper sum. So it is bounded above, right? By this one. Yeah. So this converges. And similarly from here you see this decreasing sequence bounded below by LPF. So it converges. So lower and upper integral exist, right? So this so from here what we get is the supremum of LPF over all partition exists because the limit will achieve the supremum, and so is the infimum of UPF. The infimum also achieves. So the point is that implies lower and the upper integral always exist. Now when they are equal, right? So let me mention the theorem. Oh, I don't have time to prove it, but let me state. So this is the proof is there in the notes, so I'll explain next time briefly. So do look at the proof of this theorem. This is very important. So mostly to show the equivalence criterion, we'll use this one. Sorry, this one is 3.2.4 in the notes. So a function f is Riemann integrable on interval AB if and only if and only what? For every epsilon greater than 0, there exists a partition P of AB such that the upper sum minus the lower sum is less than epsilon. If this is hold, then it's Riemann integral. Right? And it is, we'll use to show that what Riemann considered tagged using tagged partition, that is equivalent to this definition. We'll use this one. So this theorem is very crucial. Proof is not difficult. Already things are done, right? And it is written precisely in the notes. Okay, any question?
Sir, what you proved above, it's not quite showing that like this does not quite show that the lower and upper exist, right? Because here we can show that so here when we take the supremum, really we are only ranging over the refinements of P, not any arbitrary partition.
True.
So this does not say in general the supremum over all partitions exists. Like we need to use common partitions, a common refinement for that. We can't use this argument.
Which one? Yeah.
The argument that you use here is not enough to show that lower always exists, because this only shows that it always exists. Like when P1, P2, all of these range over the refinements of P.
Oh yeah. So you take any other partition, you refine this up, and you will get the same thing. That is true. So you lower and upper integral. Will show.
This does not show that supremum of LPF over all partitions exists. This shows that supremum of LPF exists over refinements of P.
That is true. That is true, right?
We use common partition, common refinement to show that over all partitions exist.
Well, so yeah. So if you look at, you have to show any other partition this is exist. Then I mean, you look at any other partition, let's say P tilde, and you look at P union P tilde, and look at the refinements. Look at the refinement of it. Okay, so that then for any other partition, the refinement will also exist, and that is a refinement of P also. So it will be the same limit, right? Isn't it?
Yeah, yeah, but this will not show enough, like to show that it exists. Like what we've shown here is not enough to show that it exists.
But yeah, right. So there is a jump here. So there is a jump here from here to here, right? So you need to look at any other partition and its refinements. Well, you don't need its refinements, or if you look at any other partition and look at, so P tilde and look at refinements. So it says actually for every partition P, and look, for every partition you have all these refinements, and there the supremum exists. So you look at any other partition, look at the refinements of P union P tilde, all right, and then the limits in this sense, then the star, let's call this star, then look at star. This will give you that this refinements, the limit on this refinements will be the same as the limit here. What do you get? So you actually get for every partition P and look at refinements, it will have the same limit. Okay, that actually proves that the supremum over all partition exists. Supremum over supreme over here, all partition exist. And similarly for UPF. So of course, there is a jump here. I have chosen one partition. What happens to other partition? And their refinements. And that is what, of course, that is why you need common refinements. That is true. Yeah, thanks for pointing this out. There is a jump here. Yeah, any other question? Okay, since there's no other question, so we'll meet again on Friday.